Hello and welcome back to Math Class in Session. Let's run through a couple of typical math, calculus level math problems, just for practice here. Problem 1. Determine the equation of the tangent to a curve at a point. That is the most typical calculus question that there is. Determine the equation of the tangent to a curve, in this case y equals 10 to the x, at a specific point 1, 10. Now I always check to make sure that the point is on the curve, because sometimes we're finding the equation of a tangent from a point to a curve. So if I plugged in a 1 here, where x is, it would be 10 to the 1, and that would mean that y would be 10, which it is. So the point is on the curve, and we want the equation of the tangent to the curve at that point. Solution. Well, in calculus, you can't go wrong by differentiating, so I decided to differentiate right away. Differentiating the curve here, y equals 10 to the x, we copy it, the derivative is 10 to the x times the ln of the base. So y prime equals 10 to the x ln 10. Now we seek the equation of a line. So let's look at y equals mx plus b, and find the m and find the b. Now to find the m, we're going to have to go to the derivative because that's the slope. It's the slope of the tangent to the curve, and it's the slope of the line. So m is this, at this point. Now x is 1, so if I plug in x at 1 here, we've got 10 ln 10. That's going to be our slope. So m equals 10 ln 10. Real simple. Now we need b. To get b, we'll plug everything into this equation. It's pretty normal. We'll put 10 in here for y, we'll put 10 ln 10 in here for m, we'll put 1 in here for x, and work out what b is. So there I've done it. I put 10 in for y, and 10 ln 10 for m, x plus b. Now therefore b is 10, subtract this. 10 minus 10 ln 10. Now I know what b is, it's right here, b, and I know what m is, that's m. I can plug them both into y equals mx plus b. So I'll just do that. Y equals mx plus b, and that's the exact equation of the tangent. But let's note that 10 minus 10 ln 10 is about negative 13.03, according to a calculator. This b value, 10 minus 10 ln 10, is about negative 13.03. While the slope here, 10 ln 10, according to a calculator, well, it's about 23.03. So we could replace those expressions, and we have the equation of the tangent to the curve at the point. By the way, this can be rearranged into different ways and equated to 0, for example. Let's do another one. A certain radioactive material decays exponentially. Well, I wonder if that's enriched uranium. A certain radioactive material decays exponentially. So it's decaying. And the percent p of the material left after a given number of years, after t years, is given by an expression. P of t is 100 times 1.2 to the negative t. Determine the half-life of the substance. Now you need to know that a half-life is a length of time. It's how much time is needed for only half of this substance to still be there. In other words, the percent is going to be 50%. So for a solution, we want P of t to be 50. So we'll plug 50 right there and figure out what t is. And that will tell us the half-life. Plug it there, divide both sides by 100. Now, in this configuration, learn this configuration. A number equals a number raised to an exponent. If you want the exponent solved, you take the exponent and equate it to ln over ln. So in this case, negative t equals ln 0.5 over ln 1.2. And that tells us on a calculator about negative 3.8. And so t is 3.8. And that would be the number of years it takes for this substance to cut itself in half. About 3.8 years. There's another part to this question, and that is, how fast is this substance decaying after this one half-life has gone by? After exactly one half-life, what's the rate of decay? How much percent per year? Solution? Well, we'll need the derivative of the expression, and we'll sub the half-life into the derivative, because let's think about it. Here's the expression. The derivative gives us the rate of change of that expression. So if we differentiate it here to get p prime of t, that would give us the rate of change. And if we could get the rate of change, that will tell us how fast the substance is decaying. And we'll just sub in the answer to the previous part of this question, and it'll tell us exactly how fast it's decaying after one half-life. And we know that a half-life, what was a half-life again? 3.8 years. So our plan is going to be to differentiate and sub in 3.8, and that'll tell us how fast it's decaying after one half-life. Priming. Well, to differentiate something like this, you copy it, and then you take the ln of the base, and the base is 1.2, so it's ln 1.2. Don't forget to multiply by the derivative of the exponent, which is negative 1. I tidied it up a bit here, so I put the ln 1.2 out front, the negative ln 1.2 out front, and still multiplied by 100 times 1.2 to the negative t. Then I plugged in 3.8. Plugging in 3.8 right here for t, and then picking up a calculator. This is where a calculator is appropriate. You don't use a calculator to go 25 squared, 625. You use a calculator for this purpose. And the calculator says that p prime of 3.8 is negative 9.12. So here we have p of t, p prime of t, I went p prime of 3.8. T became 3.8. So p prime of 3.8, the result of subbing 3.8 into the derivative, gives us a rate of change after 3.8 years. The substance is losing 9.12% per year, because this is losing because it's negative 9.12. Now it's percent per year because this derivative is dy by dx, and y is p and x is t. So it's percent, because that's p, per year, and that's t.